Welcome to Maths with EJD. As you know, in this video, we've been talking in this series, we've been talking about numerical optimization techniques, numerical optimization techniques. And so far, we have seen different methods. We've seen, okay, let me do it this way. We've seen the gradient-based methods, gradient-based methods. We've seen derivative-free methods, derivative-free methods. And now our attention goes to constrained optimization methods, constrained optimization methods. So if you remember, under gradient-based methods, we've considered three different methods. We considered gradient descent. We considered Newton's method. We also considered the conjugate gradient method, conjugate gradient method. Then under derivative-free methods, we saw the Nelder-Mead method, We also saw the genetic algorithms, Then we considered the simulated annealing, simulated annealing. Then we finally, so now we are going to be considering constraint optimization methods. And the first of that will be the Lagrange multipliers. And after that, we're looking at sequential quadratic programming. And later we'll be seeing interior point methods. Okay. All right. So for this video, we are going to be looking at Lagrange multipliers, which I think is the most popular of the constrained optimization methods. So Lagrange multipliers. So we're talking about constrained optimization and then Lagrange multipliers. So Lagrange multipliers are a method for finding the local maxima and minima of a function f of x, y, and so on and so forth. So depending on the number of variables you are considering, subject to one or more constraint equations, g of x, y, and so on and so forth equals 0. Okay, so the key idea is that an optimal point, which is the gradient of the key idea is that an optimal point, the gradient of f is parallel to the gradient g. So the optimal point is, which is the gradient, is parallel to the gradient of g, So the key idea is that an optimal point of the function. The optimal point, the gradient of f is parallel to the gradient of g, meaning that grad the derivative of the function f is equal to lambda times the derivative of the function g, basically. So this is like the standard thing here. So where lambda is the Lagrange multiplier. That's the Lagrange multiplier. Okay. So for the sake of this, I'm going to take two different examples so that we can have a proper understanding of Lagrange multipliers. Let's start with this first example, example 1. Okay. So find the maximum and minimum values of f of x, y equals x squared plus y squared, subject to the constraint, g of x comma y, which is equal to x plus y minus 1 equals 0. So we want to find that. So, okay, let me go back to this. So step 1, so for step 1, we compute gradient because see, it's all about gradients for both f and g. Compute gradients. Okay, compute gradients. So, of course, we have f already. So we know that f of x comma y is equal to x squared plus y squared. So grad of f the gradient of f of x comma y would simply be partial f partial x comma partial f partial y. And that is simply differentiate x squared plus y squared with respect to x, you get 2x. With respect to y, you get 2y. Basically, that's the derivative. Okay, so for grad, so what of g? You also need g. We have g here. G of x comma y is x plus y minus 1. Okay, so grad of g of x comma y. Okay, first of all, let's talk about g of x comma y, right? G of x comma y is equal to x plus y minus 1 equals 0. And the gradient of that, grad of g x comma y is simply, so grad g, grad x, partial g, partial x, comma, partial g, partial y. That means differentiate this with respect to x, you get 1. Differentiate with respect to y, you get 1. This is constant, so it goes to 0 for both cases. So look at the two things we have. So we have this for grad f, and we have this for grad g. Okay, so by the Lagrange multiplier condition, we know that grad f is equal to lambda grad g. Lambda grad g. So, and this simply implies that 2x comma 2y is the same thing as lambda into 1 comma 1 based on what we have got already. So we can simply say that 2x is equal to lambda and 2y is also equal to lambda, because this is simply lambda. This is simply lambda comma lambda. Okay, so 2x is this, 2y is this, or better still, 2y is this. So with this now, this simply implies that since 2x is equal to lambda is equal to 2y, okay, 2x is equal to lambda is equal to 2y. So we can say that 2x is simply equal to 2y. If you divide through by 2, then it means that x is equal to y. This is fundamental in the whole thing. So we have got the derivative that way. So we go for step 2. So we have step 2 where we solve for x and y using the constraint. So we have established that x is the same thing as y. So if you talk about the constraint, right, which is g of x comma y. So the constraint is g of x comma y, which is equal to x plus y minus 1 equals 0. So what that simply means, if you take this part out alone, it means that x plus y minus 1 equals 0. That means that x plus y is equal to 1. Okay, since x plus y is equal to 1, and we have established up here that x is equal to y, so we can talk about that since x is equal to y, then we say that x plus y equals 1 implies that implies that you have x plus x equals 1 because x is equal to y. That means that 2x is equal to 1, and then x is equal to 1 over 2. So since x is equal to 1 over 2, so we say therefore x is equal to y is equal to half, basically. So x is half, y is also half. That's what that simply tells us. Okay, so we go for step 3, and then we compute function value. Okay, so we know the function itself, f of x comma y, is x squared plus y squared. Now we have that x comma y is equal to half comma half based on what we have obtained. Therefore, we can say that f of half comma half is equal to half squared plus half squared, and that is equal to 1 over 4 plus 1 over 4. So that is equal to half in short. So we say therefore f of half comma half is also half, basically, and that goes. So we can make the statement that since the constraint defines a line. So the constraint is x plus y equals 1. So that's a straight line, right? Since the constraint defines a line, which is an unbounded region, if you plot it on a graph, it is an unbounded region. This is the only critical point. This is the only critical point. Okay. And the function does not attain a maximum. We are looking for maximum and minimum. So the function does not attain a maximum or minimum beyond this. Okay. I mean, we can demonstrate that on Desmos, but I mean, I won't talk about that right now. So in conclusion, right, we can say, thus, the function f of x comma y attains an extremum of 1 over 2 at x comma y equals 1 over 2 comma 1 over 2. Basically, that goes. Yeah, so let's talk about another example. Here, let's do this, and then let's have this. Okay. Example 2. We'll be talking about Cobb-Douglas, which is a very interesting production problem. So a firm produces outputs using labor. So labor is L and capital. So labor and capital K, modeled by the modeled by the Cobb-Douglas production function. The Cobb-Douglas production function, which is given as f of Lk equals L raised to power 0.5, K raised to power 0.5. Okay. The firm has a budget constraint, which is WL plus RK equals C. Okay. So we can say where W is the wage rate, R is the wage for labor, right? And R is the rental rate for capital, rental rate of capital. And C is the total budget. Okay. We're expected to find the optimal allocation. So find the optimal allocation of labor and capital that maximizes output. So we want to get the best production output. We need the best value of L and K that will give us the best output for production. Okay, so again, let's go for step one to do this. Step one, we define the Lagrangian, define the Lagrangian. We could do it the way we did it. I think it's better to do it the way. Okay, well, maybe this is another approach, I think. So define the Lagrangian. So it will still amount to the same thing like what we did before. So if you go through the same step like before, it's okay. So the Lagrangian in this case is a function of the labor, the capital, and the Lagrangian multiplier, which is equal to um, the objective function, which is f of L k plus lambda, okay, plus lambda of the constraint, okay. So we can call this constraint now. We can modify it to be some kind of. We can say it is g of L comma k, which is not going to be omega WL plus RK minus C equals 0. So we can have it rewritten this way, right? So this is f of LK comma plus lambda G L comma K also. All right. So we cannot if you do it the previous way, the way we did example one, you're still good. So, but here we are so this is what is called the Lagrangian. When you put the objective function and the constraint together using Lagrangian multiplier, that is what is called the Lagrangian. So this expression now is what we called the Lagrangian. This is the Lagrangian. So this is the objective function which we are trying to maximize. This is the objective function, okay, and this is the constraint. This is the constraint. And then this is the Lagrangian multiplier. The lambda itself is the Lagrangian multiplier. Okay. All right. So with this in place now, then we can go ahead and say that our Lagrangian of Lk lambda is equal to L raised to power 0.5 K raised to power 0.5 plus lambda into, of course, the first one is this, the objective function, and then the constraint is this, which has been rewritten as omega WL plus RK minus C equals 0. So we can have this in bracket here. So this is from what we have right here, right? This is so this is WL plus RK minus C equals 0. We could also, we could also rewrite this as, so if you transfer everything on the right hand to the left, okay, yeah, so you can have 0 is equal to C, 0 is equal to C minus omega L minus RK or WL. So this is another way of writing exactly the same thing. So you can have it this way or this other way here, okay? So we can bring it down here and then we have C minus WL minus RK. That's our constraint now, which is the budget, right? So with this, that's the first step right there. That's the first step. So we go for step 2. We go for step 2. I think I saw something here. This should be Lagrangian, not Lagrangian. It's Lagrangian. Okay. So step 2 is to compute first order conditions. Compute first order conditions. Okay. So what that means is we take partial derivatives, taking partial derivatives and setting them to 0 and setting them to 0. Okay, that's what we have to do here. So look at this now. There are 3 variables, L, K, and the Lagrange multiplier. So we differentiate partially with each of them. So you have, so first thing, we have, let me call that A. So with respect to L, the first variable with respect to label now, okay, we have partial Lagrangian, partial label equals, so if we differentiate this with respect to label, so the power comes under 0.5 L raised by 0.5 minus 1 times the constant, plus when you come here to L is only here, so you have lambda, you have minus W, right? Minus W. So if you differentiate that, right, you have 0.5 L raised by minus 0.5. That's 0.5 minus 1, right? Multiplied by the constant that was there before, minus lambda W. Lambda W in the sense that if you differentiate, if you open up this, you have lambda C minus lambda WL minus lambda RK. So if you differentiate this with respect to L, you get minus lambda W, okay? So that's the idea there. So we have this expression and we need to equate to 0, right? We equate this to 0. So you want to take note of that. Then the next thing is, so we have an expression like that. So the next one is B with respect to K, with respect to K. So the same thing happens for K. So K now, the attention shifts to this. So the same power thing comes down and the power of K is reduced and this is left the way it is. And then when you come here, because we are focusing on K, so we have minus lambda R, all right? Minus lambda R. So let's see. So that's partial Lagrangian or partial K, and that is equal to 0.5, 0.5 K raised by minus 0.5 L 0.5 minus lambda R equals 0. That's also there. Then we now do with respect to lambda itself, the third variable with respect to lambda, the Lagrange multiplier. So now you see here now, Lagrange is only here. So all this will go to 0. And then you have C minus. So in short, you just have what is in bracket here, because if you differentiate this, you have whatever is left in that bracket when we differentiate with respect to Lagrange, okay? So here we just simply have partial Lagrangian, partial lambda, and that is equal to C minus WL minus RK is equal to 0. So we have 3 expressions. Let me name them. Let me just say this is 1, this is equation 2, and this is equation 3. So with that in place, we go for step 3, where we solve for the variables. Step 3, solve for L and K. Solve for L and K. And to solve for L and K, we can divide. So we can divide the first equation, by the second, And you know what the first equation is? The first equation is 0.5 L raised by minus 0.5 K raised by 0.5 minus lambda lambda W divided by 0.5 k raised power minus 5. Of course, we can rewrite this as 0.5 L raised power minus 0.5 k raised power 0.5, and that is equal to lambda omega. And that will become like what exactly we did for the first example, where we just said grad F equals lambda grad G. So everything boils down to that basically. And then here we have the second expression, right? This is 0.5 L raised by 0.5 if you like, k raised by minus 0.5 equals lambda r. What I've just done is to write L first, nothing, no big deal. So if you divide the first by the second, we have 0.5 L. So we're dividing the first by the second. So 0.5 L raised by minus 0.5 k raised by 0.5 all over 0.5 L raised by 0.5 k raised by minus 0.5 is equal to lambda W over lambda R basically. So you see this cancels out. What else cancels out? 0.5 cancels out. And I can tidy up the rest of this, right? So we have so this is like L raised by minus 0.5 all over L raised by 0.5 times K raised by 0.5 divided by K raised by minus 0.5. And all of this is equal to W over R. Okay, so we can tidy things up. So L raised by minus 0.5, because of indices minus 0.5, you bring that up, multiplied by K raised by 0.5 minus, okay, minus 0.5 that was there before. And this is equal to W over R. Okay, so L minus 0.5 minus 0.5 is simply minus 1, and K 0.5 plus 0.5, that is 1, and that is equal to W over R. So what that simply tells us is that we have K all over L equals W over R. Okay, so, and we can say that L is equal to, we can say K rather is equal to L times W over R. Okay, that is what K is. We are solving for K and R. So we have got K with respect to L. So we can go further. So we can substitute into the constraint. So you see, it's more like the constraint ends up coming up as a tiebreaker. So we can substitute. So substituting into the budget constraint, substituting into the budget constraint. Okay. To substitute into the budget constraint, we see that C is equal to WL from what we have from the budget constraint. So you just need to know how to arrange it per time. So C is WL plus RK, right? C is WL plus RK. But now we got K as a function of L, W, and R. Okay. So anywhere you see K, you put L, W, and R. So C now is equal to WL plus R into LW divided by R, like this. That is what C becomes. So R cancels R. So we have C is equal to WL plus another WL. LW is WL. So C is pretty much 2WL. Now we can get L clearly in terms of every other thing. So L now is equal to C divided by 2W. Okay. So you can say that is half C over W, if you like. So that is L right there. And what else can we do? You recall that up there we got K to be equal to LW over R, right? So now we have our L now. So that means that K is equal to L. L is 1 over 2 C over W, then W over R. So this cancels out. So K itself now is half C over R, like this. Now, if we look at the Python code, we can see we can actually establish the same results from Python. This is not quite such a serious task, but when you have very difficult situations, Python comes really very handy. So, so we have the Python code regardless for this Cobb-Douglas equation using Lagrange multiplier. So, of course, we just need SymPy in this case. That's a symbolic Python. And in lines 4 and 5, we declare the variables we are using, LK lambda, WRC. These are the symbols we are using. And then We have the Cobb-Douglas equation defined in line 8. We have the budget constraint defined in line 11. And we have the Lagrangian defined in line 14. Then we need to compute the derivatives. That's what's happening from line 17 to 19. Then we have the solution right here. And for specific values, we have a line 29 where we say that W is 10. That is the rate for wage rate or something like that. R is the rent for capital also. That is 20. And the total budget is 1,000. Okay. So by the time we just run this, we see all those things outputted beautifully. Okay. Okay. I've not clicked that. Okay. So now it should work. All right. So you see, for optimal labor, the optimal labor is 0.5 C over W, just like what we got. 0.5 is half. Optimal capital is also 0.5 C over R. And then because of that, now it means that so if we substitute, so with these values we have, then we can have optimal labor to be 50 and optimal capital is 25, based on the fact that W is 10 and R is 20 and then C is 1,000. Okay, so we want to go back and check that out. So we have W 10, R is 20, C is 1,000. All right, so that's the Python code briefly. And then, of course, we can come back here and see how that works. So again, we have L is, so with W, okay. All right, we know L is 1 over 2 C over W, right? So uh with W being 10 and R being 20 and C being 1,000, the total budget is 1,000. So this is the rate for the labor. This is the rate for the capital, which is 20, and this is the total budget. So we can actually get specific values. So L is 1 over 2 C over W, right? So we have L, which is 1 over 2 C over W to be 1 over 2 times C, that's 1,000 over W, which is 10. Okay. So we see that L is equal to, if it is in dollars, for instance, this cancels, and 2 here is 1. Here it's 50, right? So it means that the rent for labor, or the wage for labor is $50. That's labor wage or something like that. And then for K, so we know K is 1 over 2 C over R, 1 over 2 C over R. Again, so we have K is 1 over 2, C is 1,000, and R here is 10. R here is 10. So this cancels. Should it be the same? It shouldn't be. R is 20, sorry, R is 20. Okay. So yeah, R is 20. So I better do that in another way. So R is 20. So 20 here is 1. 20 here is 50, I believe. Yeah. And 2 here is 1. 2 here is 25. So we see that the rent for the capital is $25, if that is what we are talking about. So with that now, we can go for our conclusion to this matter. So in conclusion, right? In conclusion, the optimal labor and capital allocation is L star, which is C over 2W. Okay. And then we have K star for capital, which is C over 2R. That's 0.5 C over R. Okay. So this result shows that the budget is optimally split. The budget is optimally split between labor and capital, with each receiving half of the total with each receiving, yeah, I think I should just stop here because this may not make so much sense. But the budget is optimally split between labor and capital. So let's just leave it that way because it depends on the values we assign. That's what we determine other things, right? So I think it's better to just leave it that way. So let's see if we can have some practice questions as far as Lagrange multiplier is concerned. Practice questions. Okay. Um, so I'll take one Cobb-Douglas and I'll take one other one. Okay, let's look at this. Um, find, that's one. Now find the extrema, minimum maximum of f of xy equals xy subject to okay okay, I'm trying to get the actual thing. All right, so find this extrema of f of x comma y equals xy subject to x squared plus y squared equals 25. That's the first one. Number two, let's talk about a Cobb-Douglas situation. Okay. A firm's production function, is f of L comma K, which is equal to L raised to power 0.6, K raised to power 0.4, and its budget is constrained by 10L plus 20K equals 1000. So find the optimal L and K. Okay. So let me see your answer in the comments, whether on Facebook or on YouTube or Facebook for sure. And of course, let me also know how helpful these videos are for you. You can also tell me if there's a topic you like me to teach or a problem you like me to solve. Then if you have subscribed, thank you so much. If you have not, please go ahead and do that because I still have so much coming. And hit the notification bell so you can always get alerted every time a new video is released. And don't forget to like and share so that more people can have access to this great content. Till I come your way again, keep doing math right. You can expect sequential quadratic programming in the next video. Bye.